Climate has made a bunch of dramatic swings throughout Earth's history, and in today's video, I'm going to be talking about a time when climate went from dramatic warming to dramatic cooling. And this was happening during the Eocene and Oligocene epochs of the Cenozoic era that we are currently in right now. But this is actually the earlier part of the Cenozoic era, the first period in the Cenozoic called the Paleogene, which includes the epochs Eocene and Oligocene, which went from around 56 million years ago to 34 million years ago for the Eocene and 34 to 23 million years ago for the Oligocene. So the dramatic warming and cooling events that I'll be talking about in today's video include the Paleocene Eocene Thermal Maximum, or PETM, which we can see in the graph over here to the right, where there's this big spike right at the Paleocene Eocene boundary, and then the Early Eocene Optimum, which I'm going to abbreviate later in the video as EEO, that's what that stands for. And this optimum happened in the Early Eocene right after the PETM. It wasn't as much of an abrupt spike as it was a broadened warming period of time. And then later, after that optimum, a bunch of cooling happened for the rest of the Eocene, mid to late Eocene, and into the Oligocene. And right at the Eocene-Oligocene boundary, there was the Eocene-Oligocene cooling, which marks the start of the modern Ice Age. These events mark a period of around 15 million years where it went from extreme warming to extreme cooling. So how did this happen? Well, feedbacks play a role. Climate feedbacks. I talk about negative and positive feedbacks in many of my videos, but I'll talk about some more later. But also other factors that we'll get into, actually. I'll keep them a secret for now. But other factors also play a role. And because of these dramatic changes in climate during the Paleocene, Eocene, and Oligocene, there were major extinctions during this time, and we'll get into those as well. So the PETM, this sudden warming event, caused both surface and deep waters to warm several degrees, even near Antarctica. This occurred in less than around 3,000 years, which for geologic timescales, that's really fast for climate change. And due to this abrupt change in climate and temperature of seawater, 70% of deep sea foraminifera went extinct during this time. And this was not only due to the warming of the waters they lived in, but also lack of oxygen. Note that I said deep sea forams, and that's because there was a lack of oxygen in the deep sea due to this warming event. That's because when polar waters become too warm to sink and provide oxygen to those bottom waters, it leads to stagnant and anoxic oceans. And I talk about this feedback mechanism in my Cretaceous paleogeography video, but also I talk in there about climate. But the Cretaceous had two major ocean anoxic events, and I talk about those and why those occurred in that video. And it was largely because of the way continents were arranged, but also because waters were so warm that the polar waters didn't sink and so on. But the rock record does suggest that oceans were not quite as anoxic as they were during those ocean anoxic events in the Cretaceous period. It's also found that during this time, carbon dioxide concentrations in the atmosphere increased dramatically, which accentuated the greenhouse gas effect, causing more warming. But what caused this increase in CO2 in the atmosphere? Well, methane release from melting hydrates was one of the major things happening during this time. And this event was so intense because carbon dioxide is more powerful, much more powerful as a greenhouse gas than CO2, meaning that it causes a more dramatic greenhouse gas effect, more intense warming than CO2. Additionally, the event was so rapid. You can see the spike was so rapid, not only in its going up, but also going down. And it was such a rapid process because methane being released from melting hydrates is a positive feedback mechanism. That just means that because the hydrates were melting and methane was being released, Earth was warming due to the greenhouse effect by the methane, and then that caused more melting and so on and so on. That's a positive feedback mechanism. A negative feedback is a balancing act. A positive feedback is a accentuating or exacerbating feedback mechanism, and that's what was going on. That was exacerbating the problem because more warming caused more melting. However, the event was quickly back to normal. We can see how sudden it is. again, because methane has a very short lifespan in the atmosphere, unlike CO2, which can stay stable in the atmosphere for a long time. Methane is not that stable in the atmosphere, only has a lifespan of around 12 years before it's oxidized to CO2, likely contributing to that CO2 increase during this time because it was, converting to CO2. And then that caused less powerful warming than methane, but for a longer period of time. However, the estimated methane release from the melting hydrates during this time, based on the rock record and models of that time, is not enough to account for all of the CO2 in the atmosphere at that time. So what else caused that? Well, low organic matter burial rates or organic carbon burial rates are likely to blame. And why were there low organic carbon burial rates? Well, because there was a decrease in primary productivity due to the lack of upwelling, due to the weak temperature gradient and weak winds during this time. What do I mean? Well, when there are warmer polar regions, like I mentioned, what that happened during this time, the temperature gradient from equator to poles is weaker, and due to this weaker temperature gradient, winds are weaker. And when you have weaker surface winds, you don't have what's called upwelling. Upwelling is a process in ocean margins where deeper, colder, nutrient-rich waters are upwelled to the surface to provide nutrients to those surface dwellers like primary producers. And because nutrients weren't getting to those primary producers, there's a decrease in primary productivity and low organic carbon burial rates. Because the rates of organic carbon burial and likely sinking organic carbon were low, that meant that bacteria could just convert all of that organic carbon into CO2 because they had enough time to, the rates were slow. And this was the cause for the excess CO2 in the atmosphere during this time. And after the PETM, temperature remained high and continued to increase into the Eocene. So remember, we're at the Paleocene Eocene boundary here, and into the Eocene, temperatures continued to soar. Even though the PETM marked a maximum, it came down after that, but it continued to go up just after that. It was just a spike and continued to spike more long-term into the early Eocene. That's why this slide is titled EEO, or Early Eocene Optimum. That's new warming event we're getting into now. Oceans were strongly stratified during the early Eocene Optimum for the same reasons as before. Warm high latitudes would lead to warmer polar waters that wouldn't sink like cold waters do today to drive, deep water circulation as well as oxygen to those bottom waters. So they remained pretty stratified, lack of oxygen in the bottom waters, lack of upwelling, etc. Also, as examples of how warm high latitude areas were, England, which has a relatively cool climate today, was coated in tropical jungles during this time in the early Eocene. Even southern Alaska hosted palm trees at the time based on the flora fossil record. And Flora and Ellesmere Island, north of eastern Canada, had leaves with smooth edges, indicating a temperature equivalent to southern California today. And Ellesmere also had large tortoises and alligators that required warm winter temperatures. So not only warm summer temperatures in other seasons, but also it had to remain relatively warm throughout the winter. And so year-long warm temperatures in these really, really high latitude regions. And unlike polar regions, tropical regions were only slightly warmer in the early Eocene than today. That meant that temperature gradients from the equator to the poles were again very weak. And air masses carrying clouds north over the forests brought a ton of heat to the northern polar regions. And these temperature gradients also accentuated the stratified oceans by lack of upwelling, as I mentioned earlier. And to go back to this forest thing really quick, dense forests covered much of the Eocene continents and land. And because of this, during the early Eocene Optimum warming trend, it was not only carbon, like methane and carbon dioxide in the atmosphere, that was acting as a greenhouse gas, but also water vapor. If you don't know, water vapor is also a really strong greenhouse gas, and that is something that you might not know just because we tend to not focus on it as much as preventing, say, CO2 release into the atmosphere and carbon footprint and all that, because we can't control water vapor as much as we control carbon release, because we are largely the cause of today's carbon increase in the atmosphere, and that's why we know we can control that and maybe help that situation. But water vapor vapor is just something we can't help. With continued warming, we are indirectly causing more water vapor to go into the atmosphere and act as greenhouse gas because things are evaporating more in warmer climates, but it's still something that we're not actively releasing to the atmosphere, so we can't really help that. But in the early Eocene, to get away from modern back to Earth history here, it was very much contributing to greenhouse global warming, just as water vapor does today. And water vapor levels during this time were kept really high because of heavy forestation. Now, the PETM changed the terrestrial vegetation patterns enough to allow mammals to make a great migration. At the end of the Paleocene, primates, ungulates, which include, your hoofed herbivore type animals like deers, cattle, horses, rhinos, pigs, etc., and members of the possum family first appeared in North America. However, quickly after the early Eocene Optimum, temperatures began to go down, and they didn't go back up for a very long time. They had little spikes, but they just continued to go down and down and down, literally until the Oligocene, and actually that transition marked the biggest cooling event of them all. But we'll get to that in a second. How do we know they went down? Well, in this graph, I should have mentioned this isn't just a temperature through time graph, but it's actually an oxygen isotope graph. And we get the oxygen isotopes, this says benthic, because we get them from what's called benthic foraminifera. Forams are those things I mentioned earlier where some of the deep sea forms went extinct during the warming event, but forams are incredible thermometers through time. And because of this, we can use their oxygen isotope ratios, which I have a whole oxygen isotope video. I'll just link it up here if you want to check it out. But yeah, we get these temperatures from oxygen isotopes. That's one way we know that it was cooling during this time after the early Eocene, but we also know because of the appearance of a genus of diatoms that attaches to sea ice showed up in the rock record right at this time, indicating the formation of ice in the Arctic Ocean. You can see at the bottom of this ice here, there's some green stuff. Well, that's algae, and diatoms are algae, so they're included in that. But because of their impression on the rock record, we can know that things were cooling enough to have ice form in the polar regions, which hadn't really happened before, at least not permanent ice. Additionally, drop stones in the Arctic Ocean and Greenland Sea rock record indicate the presence of icebergs, which come from glaciers, which means it indicates the presence of both. And so these drop stones are really helpful as well. If you don't know what drop stones are, or maybe extremophile diatoms, I have a video on glacial depositional environments where I talk about drop stones, and I'll link it up here to the top right, and also have a video about extremophile organisms that live in and on ice, etc. So you guys can check those videos out if you want to. But again, it wasn't this Eocene cooling that was the really important cooling event or major cooling event during this time. It was actually not until the Eocene-Oligocene boundary where temperatures dropped dramatically, very quickly, that marked Antarctic glaciation, or at least permanent Antarctic glaciation until modern day, that basically marked the beginning of the modern ice age. Many people think that what we call the modern ice age began only about 3 million years ago, but this actually began around 34 million years ago, or at least the beginning of the beginning. It marked the first long-term Antarctic glaciation. Ice in Antarctica grew to volumes that had not been seen on Earth ever since the late Paleozoic. But climate became not only cooler during this time, but also drier, and mass extinctions resulted from these changes. The cause of this cooling at the Eocene-Oligocene boundary is likely due to tectonic activity at the South Pole. There were 3 stages of cooling. Again, there was a stage in the middle Eocene, the late Eocene, and then at the boundary. We're going to talk mainly about what happened at the boundary. During this cooling event, cold bottom waters of the ocean developed, and this has remained until today. And this is the whole reason that we can have what's called thermohaline circulation, deep water, deep sea circulation, due to temperature, cold waters sinking to the deep ocean, and haline salt content too. High salinity waters sink as well, but cold salty waters sink to the bottom ocean and are circulating in the deep ocean, while surface waters are circulating because of winds at the surface. And it's like this big conveyor belt that's having, surface water sinking at the poles, and then it upwells at other margins. And it's just so integral to today's climate. And that's happened since this time. This is the invention of our modern ocean circulation system. But it's not only how the circulation worked, but also the actual circulation pattern because of how the continents had shifted during this time. What do I mean? Well, movement of Australia away from Antarctica. Remember that when we talked about Cretaceous continents and their positions, Australia and Antarctica were basically one big mass. Well, in the Eocene, as this globe up here shows, Australia had started breaking away from Antarctica. And then in the Oligocene, it began moving further away. This was key, along with the opening of what's called the Drake Passage between South America and Antarctica that formed the circumpolar current, basically the current that goes all the way around Antarctica. Waters from the South Atlantic, Indian, and South Pacific Ocean become trapped in this current, progressively cooling while cycling around Antarctica. Warm waters were no longer directly transferring warmth to Antarctic waters. It was cooler waters that cycled around Antarctica, keeping themselves cool and progressively becoming more cool. As Australia moved further away from Antarctica, the Drake Passage deepened and the current strengthened, leading to further cooling and glacial expansion. A decrease in atmospheric CO2 also contributed to the cooling at the end of the Eocene. This decrease was likely initially triggered by the cooling of the circumpolar current. And that's because cooling reduces atmospheric CO2 by increasing organic carbon burial with three positive feedback mechanisms. One, an increase in primary productivity. High primary productivity rates increase organic carbon burial because more organic carbon gets past the decayers, the bacteria. And this was accompanied by a reduced rate in bacterial organic matter decay. I talk about the conditions that favor organic carbon burial or hydrocarbon preservation in my hydrocarbon preservation video. If you want to check it out, I'll link it up here to the right. The third positive feedback mechanism, though, was formation of methane hydrates. The cooling increased the formation of methane hydrates that, could freeze and not continue melting, and that caused more methane to be trapped in the hydrates so that it wouldn't be released to the atmosphere and it wouldn't convert to carbon dioxide, etc. So it was just more sinks for carbon, and that just ultimately reduced the carbon dioxide in the atmosphere. But life doesn't just undergo extinctions when it comes to warming. Abrupt cooling events can also lead to major extinctions. Many species became extinct due to the first two stages of cooling in the Eocene, but the major mass extinction event wasn't until the Eocene-Oligocene cooling event at the boundary. Marine life was especially hit hard during this cooling event because, again, ocean temperatures and circulation was pretty much changed forever, at least forever till the modern day. For example, warm-adapted species that thrived during the Paleocene to the mid-Eocene time went extinct because they were adapted to the warm period. These include spiny planktonic forams or foraminifera, those guys that gave us the oxygen isotopes to make the temperature graph. They also include many species of coccolithophores and many species of benthic mollusks. But there were major terrestrial changes too, including major terrestrial flora changes due to not just the cooling. In fact, it was more so due to the aridity, the dryness, the increase in dryness, than it was the cooling. Because like I mentioned, during the warming events, tropical and subtropical forests were all the rage. They were covering everything. Most of North America and Eurasia were covered in tropical forests. So without moisture, when it became dry, what are those forests to do? Well, during the Oligocene, dry woodlands with large grassy clearings dominated. And this was a positive feedback. Forests held more moisture and had lower albedo. Lower albedo means lower surface reflectivity. They held in heat. So with deforestation, things became cooler because there was a higher albedo, higher surface reflectivity than the forest would have provided, and also held less moisture, so drier. So deforestation that was caused by cooling and drying increased cooling and drying, aka positive feedback. The cooler oceans also contributed less water vapor to the atmosphere than they did during the warming times when they evaporated more. So all these things were positive feedbacks leading to more cooling and more dryness. These terrestrial vegetation changes led to the extinction of many mammals, such as tree climbers and herbivores whose teeth required soft leaves. However, new Oligocene species had molar teeth that could grind coarse vegetation that the new open terrains of the Oligocene had available for the animals. So those guys, became more abundant and thrived. The open ecosystems also caused a transition from medium-sized herbivores to large herbivores with increased stamina so they could outrun predators in this new open terrain. Also, many new kinds of rodents and rabbits could burrow and find cover in low vegetation. Since the Eocene, forests have never again been that widespread. That was the most densely forested that Earth has pretty much ever been. And grasslands, on the other hand, have continued to occupy broader and broader regions. So our climate has been moving away from dense tropical forests to a more grassy or dry woody type of, environment. And this Eocene-Oligocene boundary actually is often regarded as the shift into Earth's modern environmental regime. I wonder when the next shift will be. Yes, maybe that was a slight dig at humans. Okay, that is all I have for today's video. If you want to check out major reference I'm using to make this and many of my Earth history videos, I am using Earth System History, which is linked down in my description if you want to check it out, and upcoming and or related videos in this series of Paleogene videos includes Paleogene life and Paleogene tectonics, and they may or may not be out by the time you're watching this. Don't know what order I'll put these out, but they'll also be in my historical geology playlist if you want to just click that playlist to watch those videos or any other video that I have about historical geology or events in Earth's history. And with that, guys, thanks so much for watching, and I will see you guys next time. Bye.